Now we come to our final example. Suppose f is a continuous function over this closed interval. Okay, then we have this result. F is a single variable function, but the variable of f, we can assume that the variable of f, t equal x plus y. Then you replace the t. Actually, this is a composition. ft, z equal to ft, and t equal to x plus y. So the composition is a function of x and y in this way. Z equal to fx plus y. This function is the composition of z equal to ft, and t equal to f plus y, x plus y. So anyway, this is, although f is a single variable function, this is two variable functions. So we compute the two variable functions over this domain. The double integral of this, we compute the double integral of this two variable function over this domain. And the result is that this integral will equal the definite integral of f as a single variable function. Okay, so how to do this? So whenever you encounter a problem, no matter computational or some statement need you to prove, you need to make it clear what the integral domain is. Okay, now, so this is the domain. The vertex of this is 1 0 0 1 minus 1 0 and 0 minus 1. The right picture. Okay, so our integral domain is bounded by this picture, because this line is x plus y equal to 1, and then you go here, and finally in the lower boundary you will get x plus y equal minus 1. That is the absolute value of x and y, the sum of absolute value of x and y is from minus 1 to 1. Okay, so this is the domain. Absolute value of x plus absolute value of y will not greater than 1. So this domain, the integral of f x plus y over this domain can be easily computed if f is given, because this is of course this is not a rectangle. Anyway, this is a rectangle, but it is not in a very nice position. Okay, so we cannot, if we apply the Fubini theorem to the integral, the integral domain is not a very nice rectangle, because the edge of this rectangle is not horizontal or vertical. It is in a direction of 45 degrees. Okay, so this is the problem. So how to prove this equality? Our idea is to make a change of variable, because for x, y in this domain, x plus y lies in 1 and minus 1. And x minus y also lies from 1 to minus 1. So this motivates us to introduce, denoting our domain by d, then our omega, we take an omega to be this rectangle. That is the rectangle in blue. This is a very nice rectangle in the right position. Okay, so then define the map, transform uv to xy. The map phi is given in this way: x equal half of u plus v, and y equal half of u minus v. You subtract v. You will see that this phi transform maps the omega into our to be the D. So that is phi is a diffeomorphism. Both omega and D are open. Therefore, it makes sense to talk about whether a map between them is a diffeomorphism. So you can see that our phi is a diffeomorphism. It is elementary to see that this phi is 1 to 1 and 1 2. So this is a bijective. And also it is smooth. The partial derivative of phi with respect to u and with respect to v exist and are very good as continuous. Okay, and also the Jacobian determinant. We can compute the Jacobian determinant. That is the determinant of this matrix, consisting of partial derivatives of x and y with respect to u and v. So this is quite easy a computation. The derivative of x with respect to u is a half, with respect to y is also a half. Similarly, the derivatives for y with respect to u and v. And this determinant is minus a half. Easy to compute. Now, having convinced us that this phi is a diffeomorphism between D and the omega, okay, and also computing the Jacobian determinant of this map, we can apply the change of variable formula to get the integral we want to evaluate. That is the integral over the domain D. Can be replaced or written by transform into a new integral over a new domain, that is our omega, of the new integrand. The integrand is to replace the expression of x and y into the integrand fx plus y. So x plus y is half of x is half of u plus v, y is half of u minus v. So x plus y is precisely u. Therefore, we obtain the fu here. And this absolute value of minus a half comes from the absolute value of the Jacobian determinant required in the change of variable formulas in our theorem stated at the very beginning. Okay, so so the absolute value is a half. Therefore, this becomes a half of the integral of fu over omega. Although f is a single variable function, how to compute the single variable function which is over a two-dimensional domain? This is a very tricky point. Some students could not understand. As we know, a real number has no variable, but you can consider it as a one variable function. Okay, only if it is not explicitly dependent on the variable. Similarly, a single variable function can also be considered as two variable functions. Okay, it simply depends on u, not depend on v, or given u, for every v, the value of the function at uv is fu. Okay, so single variable function can be considered as second variable functions. Okay, so now this integral, the integral domain omega is now a rectangle, a very nice rectangle which the edge parallel to the coordinate axis. So when we applying the Fubini theorem, the lower limit and the upper limit of the integral are constant. So this is make the computation of the integral very convenient. Okay, so using Fubini theorem, this integral can be written in this iterative integral. Firstly, we have to integral with respect to u first, because the integrand depends on u. So we integrated with respect to u first and then v. But the inner integral does not depend on v. So after integrating with respect to u, this is a constant that's not depending on v. So it can be moved out of the integral with respect to v. But the integral of v is the constant function, the integral of the constant function over minus 1, 1. Therefore, the integral of v is 2. So this 2 cancel with the 1 over 2 in front of the integral, give us the final answer is the definite integral of f over this interval minus 1 to 1. Okay.